about photonic crystals, Kim?
What is one child slowly adoption?
Does someone drop their pencil in front of you and just like...
1500 Kelvin is really hot.
So cool, awesome.
We're supposed to be learning, Kim.
Wasn't there a solar? Wait, you guys think I'm remembering?
And can melt what?
materials. I can totally dress. Yeah, I can handle it, like, or heels, or like putting on makeup, or like. There's no way I could ever wear heels. Shut up.
You were on recording.
What did you just?
Callum, why are you recording me?
Is it everyone?
What are you doing? Why are you recording me?
I think we're gonna move on for a minute now. Before we get into like what I think is awesome about this stuff, does anyone have any questions about things that were not clear, things that were confusing when you read through this website, pictures that didn't make any sense? Yes?
What is a photonic crystal?
Yeah, so a photonic crystal is a material that will only absorb specific types of light. So most materials absorb at least partially all kinds of light. Everything has some preferences, but in general, most materials absorb almost everything. Photonic crystals are really unique in that they entirely reflect specific wavelengths and then entirely absorb other ones. So if you think of light coming in and hitting something, generally some of it goes into the material, some of it bounces back. Photonic crystals, for maybe all of green light, it will just entirely be reflected, but all of red light will entirely be absorbed. That's what makes them unique relative to sort of a normal material. And that you can use that in these sort of solar power applications. And I guess if there's more questions, otherwise we'll kind of move into that solar power aspect of it. So does anyone have a question? If not, let's go back to this worksheet. What was one cool thing you found out about photonic crystals? Or one cool thing you found out about solar power that you'd love to share with us? Yeah, they get really, really hot. 1500 Kelvin is, it's said on the website, it's like 3 or so times the boiling point of water, more than that, times the boiling point of water. It is an incredibly hot, it would melt most materials. It would burn you very, very quickly and very, very badly. It's hard for me to like comprehend and like give you a good example of something else that's that hot, because there's nothing I can think of that is like, this is really, something's like, lava. Well hotter, yeah, lava is really hot. Most metals melt below 1500 Kelvin though, so, or many metals do. And so some lava might be cooler than that. I'm not entirely sure what the temperature of lava is, but it's kind of a good, yeah, which would be about 1500 Kelvin. So yeah, it's about exactly what lava is then. So if you picture these things as lava only solid, that's the temperatures we're talking about. Any other cool things about these materials you found out?
I'm way hotter.
Okay, let's kind of go around the room.
Take that and divide that by 30,000 now, and then you'll find out how
cool
hot
fact
it
you learned. Nothing cool. Pour my soul into this website. You have nothing for me.
I wrote down what you said, that they absorb wavelength.
Yeah. I mean, I think that's really cool. I think that like the fact that you can make a material that behaves unlike natural materials is kind of a weird thing that physics allows us to do, that allows us to improve on sort of all of our technology. I think that's a really cool thing. So that's a great answer. Yeah.
What's the color of a photonic crystal?
So the crystals themselves can be any color. It depends on the material they're made of. Most photonic crystals, at least modern ones, are made of tungsten, which is, I believe, a black metal. Generally, although when it heats up, it will turn red, like most materials. It'll get a lot redder as it heats up. But just think of it as a normal metal. They're not made, the materials themselves are not special. What makes a photonic crystal act the way it does is the pattern you make them in. And so photonic crystals, particularly tungsten ones, tend to be kind of a giant square grid with little tiny holes drilled in it, but like tons of little tiny holes in a repeating pattern. But in the end, it's just a big piece of metal. Yeah. That's a great question, though. Do you have a cool fact for us? Cool thing, something exciting, something you learned?
Everybody stole mine.
Maybe this table. Do you have anything exciting?
Like a shorter wavelength, have higher energy than light.
Yeah, definitely. So this is something that like didn't make a lot of sense to me for a long time. It's sort of a weird thing to think about. But the fact that wavelength corresponds to energy, I think, is both kind of unique and kind of cool. And also, you generally think of things that are like longer or bigger often as having more energy or being more powerful. And with light, you're sort of talking about the opposite. You're talking about really, really short wavelengths having all of the energy. And why that is a little bit complicated, but more or less has to do with the number of peaks that hit something. If you picture light moving as a wave down and along, you're talking about each peak that hits, we'll say, is like 1 unit of energy. And so if you have more peaks over a short distance, you have a lot more energy. It's kind of a good way to think about this, kind of a basic level. But yeah, I think that's really cool. I think that like the fact that you have light, it's one object, but energy is determined not by how fast it's moving, because light moves at the speed of light, but by how long its waves are, is kind of cool. Anyone at this table have something you learned? Yeah. Yeah, so this is like why I think that solar power right now, I think solar is an awesome idea. I think getting energy from the sun is really cool, and I think that renewable resources in general are kind of the wave of the future. But right now, solar power isn't very good. We can only get 33.7% of, no matter how great a solar cell we make, we can only get about a third of the energy, and that's just not very much. Most of our like fossil fuels are more efficient than that. It's so much easier to get energy from other sources, and we're just not very good at getting energy from the sun at this point. Which is why I think photonic crystals are awesome, because they can make that better. Does anyone remember what the percentage for a photonic crystal, a good photonic crystal system is? 80%, right? That's more than double. That's really, really efficient energy. That's like, if we got 80% of the energy from the sun, even in like a really small area, that's a lot of energy. I mean, the sun is a very energetic source. It is a giant ball of fire, effectively. And that's a lot of energy, and that's something we could power us in a way that like most other things can't. Great. You guys? Good. Yeah. So it turns out that's a great segue kind of into the second question. So why aren't these things being adopted now? What are the kind of the challenges facing us? Does anyone remember any of these challenges? And that will get to the question of why we only kind of have 10% efficiency. Does anyone remember some of the reasons why it's hard to make photonic crystals? Yeah.
Because you need to make them durable enough so they don't melt.
Right, so 1500 Kelvin, as we talked about earlier, is the temperature of lava. That's really, really hot. And we can't have things that are, if we make it out of materials that, I mean, certainly many metals will melt at that. I mean, rocks and molten lava melts at that temperature. So we need something that's going to be really, really strong and able to withstand these high heats. Anything else? Any other reasons why these things maybe are hard to make? Sure. So when you're putting does anyone remember something about maybe having two materials next to each other and what happens to those?
The change in the temperature?
Yeah, so as things get hotter, they expand a little bit, and as things get cooler, they contract. And if you have two things next to each other and it expands and contracts, you start to kind of wear along that border. And all of a sudden, what was like a really kind of a durable system between two things, you start to get cracks in it, they start to shift apart. It becomes really hard to transfer the heat from one to the other. They just kind of break down. Exposing things to stress is just really difficult when you take a glass. When I was in maybe in 5th grade, I took a glass out of the dishwasher in my house, and it was really warm because the dishwasher uses really hot water. But I wanted cold water in my glass, and I wanted my glass to be colder, so I stuck it in the fridge, and it just got these massive cracks up and down the side. Because when you get something from really hot to really cold, it just starts to break down. And those sorts of things happen with photonic crystals, but on a much bigger scale. You're talking about way hotter materials. And while the change in temperature is slower, you're still causing a lot of expansion and contraction in these things, because you're going over range from at night, probably room temperature, or at least the temperature of the outside when there's no sun shining on them, to molten lava temperature during the day. And that's a big range. Awesome. So I think that kind of tries to get to the question of why we're not very good at making these. They're also just really, really small. So it's really hard to make, when you make these little circle patterns, those circles have to be around the wavelength of light, generally half the wavelength of the light you're looking for. And so light is at least in this instance, is about, we're talking maybe a couple micrometers. So does anyone know what a micrometer is? In sort of how many micrometers are in a meter?
It's
10 to the 6.
10 to the 6th, yeah.
Yeah, 10 to the 6th. So that is, if you think of a millimeter, there are 1,000 of them in a millimeter. Yeah, I did that correct. Okay, there are 1,000 micrometers in a millimeter. These are really, really tiny things, and you're making them on the scale of one of those. And it's really hard to make things that are durable that have holes at that width with little tiny, ridges between them. And so these things just kind of break down, particularly when you're expanding and contracting them, but even just in general, these are fragile materials. These are really, really finely tuned, high precision made materials that can just kind of break. And it's hard to do that. And I think the final answer to why they're only at 10% has to do with heat loss in general. That just, that diagram was kind of a cool diagram where you had all of the wavelengths coming in and only one specific wavelength coming out. But realistically, both materials are emitting at that point because heat is just flying off of these things because they're in air. And it's hard to kind of keep the heat trapped in these crystals. And so as you lose heat into the air, until we have a better way of keeping the heat in the crystals, they're going to lose efficiency. Yeah, so any other, I think we covered kind of a lot of the challenges. Does anyone have any, I guess maybe not final thoughts, but like reasons that you think photonic crystals will or will not kind of be cool in the future? I mean, do you guys think that we're going to be able to design these things in the future that we'll be able to have better solar power? Do you think we're kind of stuck where we are? Yeah.
Since you say they're so delicate, how come they don't, how are they supposed to make them, work in the weather? What if it's hail or tornadoes or wind?
Yeah, so I think there's kind of two parts of that. And the first part is they're going to be encased in something, probably like a transparent layer. So current solar cells right now generally have a layer of a hard plastic over the top of them that prevents them from when hail comes down, you're not actually hitting the solar cell itself. You're hitting kind of the casing on them. Light gets through the casing because it's transparent, but the weather shouldn't get through. In the instance of a hurricane, if you're really throwing these things or ripping them out of the things, they're probably going to break. But for normal weather, you can design kind of hard shields that will be able to protect them. And even kind of a great example is just if you think of a hockey rink, they have that shatterproof glass over the boards, and you can hit that stuff really, really hard, and it's not going to break. And what's underneath isn't going to break. If you give it a little bit of space between that, you're going to be able to protect these things. They're not going to get jostled around very much. And if you do that, and you kind of encase those in that material, you have a really great way to protect them from at least most common elements, maybe not everything everywhere.
Mm-hmm.
Yeah. Anyone else with questions, thoughts? Going once? Going twice? Yeah, so I guess what I kind of want to leave you with is just this idea that right now, as we move forward in the world, as we move forward away from fossil fuels in particular, wind and solar energy are becoming really popular ideas, but they're not very effective now. Everyone always complains that wind power and solar power cost too much. And Carleton, for example, has 2 wind turbines, and we get a lot of our energy from those, but we can't power the entire college yet. And it's going to be hard, and it's probably going to be, particularly if kind of the big power companies use these, it's going to be more expensive to get energy from those than from coal. I mean, one of the reasons that is because of this lack of efficiency. And so as we start moving towards new technologies to make solar panels more efficient, as we move towards photonic crystal systems maybe other ways to get, instead of 30%, even 60%, or 80% would be awesome, although I think that's a little bit more long term. But as we move in that direction, we'll be able to make all of these technologies people love to talk about but don't actually love to build, things that we can have. We'll be able to have solar panels on your roofs that work not just when you have a massive array, but even in small quantities. We'll be able to make real differences in the amount of energy we're able to produce just using simple technology like these. I mean, these systems themselves are not complicated to set up. It's maybe difficult to build a photonic crystal, but all you need to do is stick it in front of your normal solar cell. It's not any more difficult to set up. It's not any less durable than a normal system. And in many ways, that's kind of, I think that is what makes these so exciting, that we're moving towards, as we get towards renewable energies, this is going to be the way forward, I think. This is the way that we're going to be able to take ideas that everyone has, ideas that everyone loves to talk about, and make them something we can use to actually power our future. And that's why I love photonic crystals. And with that, I think there's very little time left in this class, so I'm going to stop talking. But if you guys have other questions, and you just want to write them on the back of those forms, and maybe give me an email address, I'll be able to answer them. If